Hello everyone. In the unenvious position of trying to explain polymorphism right now because it's so hard to thread this particular needle, and hopefully I'm not going to have a flicky screen like I did last time. Let's just move to the next slide. There we go. So we're going to be talking about the final piece of the puzzle for why objects are and classes are so powerful. And I like sort of going with an analogy, or like going with an example actually. And this will actually go directly to what we're going to be doing in one of the next assignments. When we look at model view controllers and events, we'll be doing a drawing program, a painting program. And you'll just draw little shapes with your mouse onto a blank canvas essentially. And I will say, just to warn people in advance, there will be a lot of my code given to you guys. Hopefully it will be self-explanatory, or at least we'll talk about some of the code beforehand, but I want to make sure that people are aware that there's no real avoiding this. If you try to do it all by yourself, it's like a 4-week assignment. Or I could give you a whole bunch of boilerplate code so you don't have to figure it out, and I say look at these particular sections because oh my god, you're going to die otherwise. So hopefully that's going to make your life easier, but I apologize in advance because I know a lot of people wanted the code, not given the code, and to draw it up themselves. But in terms of events, in terms of painting, there's a whole, I get confused, and I've been programming GUIs or graphic user interfaces for years and years and years. I guess 20 years. And yet I still have to look up how to do half this stuff. Right? It's just so much fiddly diddly crap that's nothing to do with the course. I don't want you getting stuck into that particular unenviable situation. So I'm supplying the code simply because I don't want to punish you guys with the nuances of GUI design and GUI development. Okay, so we're hopefully going to have a clear layout of where things are, how things are working, and I'll also talk about it now. So we're going to look at inheritance again, and then talk about how inheritance and polymorphism sort of work together. I'm going to show you an example of us drawing different shapes. I'll look at this. Actually, let's look at it now, and how all of this fits together. So let's bail out of this. Let's open up. This should actually be the assignment itself, or at least the assignment was for last term, and hopefully everything's ready to go. So let's compile it again. All right, didn't need to compile it. There you go. Let's run my program. Here is what the program will eventually, or hopefully, look like. I draw a shape. I get a rectangle. Okay, I can draw another rectangle if I want. When the mouse moves over the rectangle, I fill it in. Otherwise, it's unfilled. I can also use Shift and click and drag. This is a click and drag motion. So I click down here, drag, and lift up. And when I lift up, I make the shape. On the lifting up the shape. Okay, here's me making a circle. I can even move these things around. Notice I have an outline for when I've selected something. All right, and I can do control, and that'll give me a triangle, for example. Move that around, and control and shift together at the same time. I had it do an arrow. That's not part of the assignment, but you can have it do all sorts of things. Okay, so I'm making a series of shapes. What I don't want to do is have to figure out what kind of shape I just drew. So I have to figure that out at some point in time. But the application here should not have to know that I am drawing a rectangle here. What I really want is to have just a grab bag of shapes that I've drawn. I just have an array of shapes that I've drawn, or a vector if you want to use a vector. I have just a big array of shapes, and I go to each one of those shapes and just say, draw yourself, draw yourself, draw yourself to each one of them. And then I want to go to them and say, by the way, there's a mouse event. Deal with the mouse event, and tell each of the shapes, deal with the mouse event. I want to go up to each one of these shapes and say, update yourself, and they all update themselves. This is what we're going to talk about when we look at model view controllers, the separation of concerns between what's drawn, how I update the data or change the data, and how I deal with user input and output, or user input and controlling events. So that could be a timer goes off at a certain interval. It could be a mouse event happens. It could be a keyboard event happens, like I type something on the keyboard. I want to separate those concepts out into individual, like I want to have completely different functions, and the different functions don't, communicate with each other. So when I deal with a mouse event, I only deal with a mouse event. I don't go painting things. I don't go updating how things work on my system. I just deal with the mouse event. And then afterwards, I might deal with, how things would change. Like when I hover over this, the repainting of this is a different event. So when I want to repaint this rectangle, when the mouse moves over it, that's a different event. It's a painting event. And we go one step further and say, when I'm the thing that paints my shape, the thing that handles my mouse events, the thing that handles the logic, are three different classes. They're sort of a holy trinity, if you will. I don't want to be sacrilegious here, but they're like a trinity where, like religion, Father, Son, Holy Spirit. If you're a Christian, the idea that you have three things in one, they're actually one unit, but you consider them three completely different classes. So the three classes are considered conceptually one thing. Okay. I also want to point out we have events when the mouse moves in any way, shape, or form. If the mouse goes down, if the mouse comes back up, if I move the mouse on the screen at all of these cause an event to be fired. The operating system has an event, and I have registered to listen to those events. What you tell the operating system is, when we have this kind of event, send a message to my function. Much like when you're on a waiting list for something, or you're trying to get a text back when something becomes available, like a library book becomes available, or pretty much you name it, right? We have a lot of things where we're waiting for an event. When something updates or when they've changed something, you get a push notification, right? So this idea is, if I have a mouse event at all, it gets sent to my main application, and I process or deal with the mouse event. It gets sent to one function, that function deals with it. When I get told to repaint things, a paint function gets called, and I deal with it. When I have a timer event, the timer goes off, and I deal with it. I separate I'm getting these events. I register to listen to events, and when those events happen, like a mouse gets moved, then I get a callback. Okay, so I move my mouse at all, I get a callback. The issue is, I don't want to have a list of the rectangles, and a list of the circles, and a list of the triangles, and a list of the arrows, and if I make 5 other different types of shapes, 5 other different arrays for all the different shapes. What I want is just an array or some kind of listing of all the shapes. And they all draw themselves correctly. They know how to draw themselves, and they draw themselves correctly. Okay. So that's the concept here. Let's look at some code here. So what I have here is a parent class called Shape2400. The shape class, do I have it here? There we go. The shape class, you can do some painting. I'm going to actually change something right now for the next demonstration of this. And it can paint an outline. Notice I separated the view, the controller, and the model, which is here. And they're all under one. You can throw them all in one file, essentially, if you want to, or you could separate them into 3 different, 6 different files, 3 CPP files, 3 .h files, or you can shove all 3 into one file, depending on how you want to view this. We'll talk again more about this. I want to have multiple exposures to this idea. But the Shape2400 has a particular bound, so where dimensions of the shape is. Do I focus, as in, am I hovering over with the mouse? Did I select it? Did I click on it with the mouse? Do I have a background color? What is the background color? Am I intersecting, or can I figure out if 2 things are intersecting, for example? I can set the particular bound for the shape. I have a constructor for my shape. I can get the background color. I can tell if it's selected. I can move it. These are all just things for controlling the data representing the shape. The view knows about this shape, can get information about the model, the data itself for the shape, and can draw accordingly. All I have is paint, essentially. And so when I go to paint, I say, hey model, what's your data? Okay, I now know how to draw this thing. My controller, same thing. I'm going to have, hey model, what's your data? Now I know how to deal with mouse events, for example. This is model view controllers. This is another lecture.
I found this on the web.
And my phone is answering for some reason, despite not saying anything at all. Okay. So here's the kicker. What I want, let's go to my, where is it? My main. Do I have an example of that MVC canvas? I think that would have this. What I wanted is just, let's MVC canvas .h over here. And we'll look at this in terms of the linked list as well. I just want a big old array of all the possible, like I have a maximum number of 30 shapes I can draw on the screen. I want arrays of these, like a shape, a controller, and a view. I just want arrays of these things. That's what I'm aiming for at the end. I just want these arrays of shapes. I don't want to know if it's a rectangle or a triangle or anything like that. I just want it to draw itself correctly. Okay. So my options are, I have arrays of an array for all the rectangles and an array for all the circles and an array for all the triangles. That's ugly. Especially if I add another shape, I don't have to change all my code. That's a pain in the ass. Okay. If I don't want that, what else could I do? Let's go back to my PowerPoint because that's going to hopefully make it easier. If I don't want to just have different arrays for all the different shapes, well then what I need to do is I'd have to have a function, a paint function for the shape. And because we have a paint function for a rectangle and a paint function for the circles and paint function for triangles, I could have different function calls and say, hey, by the way, are you a rectangle? Okay, I'm going to call paint rect instead of paint. Okay, that's ugly as heck. That's horrible. Or I could say, oh, I'm going to cast it. I know you're not just a shape 2400, you're a circle 2400. Instead of a shape, calling the generic shape painting method, I'm going to call the circle painting method, and I cast the object. Instead of it being just a shape 2400, I'm going to cast it to being a circle 2400, a child class of it, and call paint, and then I'd get the right paint method. Again, that's really, really ugly. So here's me drawing a bunch of different shapes, but if I want to know how these different shapes, if I have different types of shapes, different colors, different sort of things like that, I just want to go to all the shapes and just say paint yourself. And I don't want to have to know, none of my code should know what kind of shape it is. That sort of breaks down the concept. If I have to manually cast things over to being a circle 2400, it's ugly. So I want all shapes to be called. I don't want to have to cast things. And currently, we need to cast things. If I want the circle 2400 paint method, I need to go, no, it's not a shape 2400, it's a circle. Like what we did with malloc, where we have to cast every single damn thing that came our way. No, it's not a void pointer, it's an integer pointer. Every time we called malloc. What I really want is call paint on everything and it works. No casting, no nothing. The only thing that should know about what it is the actual object. To take it into another analogy, if you're a Carleton student, the administration does not want to have to know what each and every one of your degree programs are. The individual student should know their degree program. The individual student should know the special circumstances that they have. The Carleton has some information about you, but they don't need to know all the information. When they ask you for something, like let's say your home address, you tell them your home address, irrespective of what kind of Carleton student you are, what degree program you're in. Ideally, the object knows about themselves. They know the degree program. They know the special circumstances that they are under, not Carleton. So the Carleton does not want to know that the net program people, or actually all of you guys, have to go to trek up to Algonquin most of the time. They just don't want to have to. Like, they want, okay, I'm going to schedule my classes. Their Tuesdays are free, but Carleton, as an administration, does not need to necessarily know why your Tuesdays are free. Let's say, actually, your Mondays and Wednesdays are free. They just want to be able to say, look, we're not scheduling classes on those days. Polymorphism says, essentially, you get to choose, depending on the Carleton student, you'll have a different circumstance for that person, but that does not mean that Carleton has to know about it. The individual knows about what they need to do. They know what the right call is. So, the term polymorphism actually is Greek, and it literally means many forms. Poly, many, morphism, form. And strangely enough, polymorphism itself is polymorphic, as in it has multiple different formats, multiple different forms in itself. We will look at four different sort of types of polymorphism. So polymorphism is polymorphic. Not ironic at all. It's actually kind of cool. The key is what function you call. Since we have many forms, what function, what way you interpret the data depends on the context. It's not a random guess. It depends on how it's called. And this is to make your code modular, makes your code simpler. You don't have to rewrite code. You don't have to use a whole lot of boilerplate code, and you can reuse a lot of code. We will also look at the doubly linked list and linked list classes to help illustrate this as we go along. So, here are the four different types. We have what's called ad hoc polymorphism, or overloading. So we may have seen some of that already with our constructors, when we had two different constructors, and sometimes this one was called, and sometimes this one was called, or we had two different versions of a function, and it depends on what the parameters calling this thing were, depended on which function was called. So I'm trying to think if strings had that. Strings definitely had that. You may not have realized that they were doing that. The string class, if I pass in a C string, like a character array, to a string and I'm appending it, it works. If I pass it in a string object, it works. They're two radically different things. Yet, you just think when I call append and I pass in some kind of string, either a C string or a normal string, it just works. That's an ad hoc polymorphism. And which function gets called depends on the input parameters. Okay. We also have coercion, or casting. So I say we did this with malloc, right? It's a void pointer. No. I'm explicitly stating it's an integer pointer, let's say. It's when I put those parentheses in there and say, look, no, you might think it's a void pointer, but it's actually an integer pointer. Or you might think it's a double, but it's actually an integer. Casting. It could be implicit or explicit, depending. We have parametric polymorphism or compile type polymorphism. This is more like our templating. We'll deal with that much later in the course. Templating allows you to put in data of various types. If you've ever used the vector class, you've seen templating before. It's the ability you can make a vector that stores integers, or you can make a vector that stores strings, or you can make a vector that stores, whatever the case is, a variety of different types of data via this particular mechanism. And then when we get to real, quote unquote, real polymorphism, that's type number 4. That's runtime polymorphism. Okay, so here's overloading. If I have a rectangle class and I have a function that's called setBound, in fact, we have a function called setBound for our shapes. You can either take in an x, a y, a width, and height, coordinates, or you could just pass it in a rectangle. I would have two different definitions of setBound. They're completely different. They look different you write the function twice. Once with these 4 parameters, once with a rectangle data structure instead, or rectangle class, I guess. And which one do you call? Well, if you call setBound with 4 numbers, you're calling that one. If you call setBound with one value and it's a rectangle object or a rectangle structure, depending on if it's a structure or object, but you call setBound with a rectangle, then it calls this one. Depending on the circumstances, how this gets called, the function maps to what how it's being called. Which one gets called? Well, it depends. We saw that with our constructors. If I can have a blank constructor. I can have a constructor that takes parameters, and which one gets called depends on how I call new. And we also have, strangely enough, and I'll show examples of both of these actually in a second, we have operator overloading. This is something that, if you're used to, let's say, Java, blows a lot of people's minds, because you don't do this in other languages. C merely lets you override and replace what various operator symbols do. I can define what the plus symbol does for a rectangle. So you pass me, I can say rect1 plus rect2, and it will call this function using rect1's. This rect1 will call this particular function, the plus operator. It will take in a parameter, which is rect2, and it will do whatever that function defines the plus operator to do. So in this case, it might be the union between rect1 and rect2. So the rectangle that binds both rectangle 1 and rectangle 2. We've done this with strings. Strings actually did this, and we didn't even bat an eyelash. Hello plus world gives me hello world. That is not math. That's concatenation. It's radically different than a number. Hello plus world gives me one string with both of those, with all that text in there. It is not the same as 4 plus 7. Right? They are radically different. I overloaded the plus operator to do something different for strings than I did for integers. So we could do something with the shape operator. I'm going to do something with the linked list operator for overloading, and I'll show you that in a second. So the shape operator, if I had a shape and I wanted to figure out the area of a shape, I could have an area function, and what I would expect for the greater than operator would be I calculate the area for one shape, I calculate the area for the other shape, the parameter shape, and I return which area is bigger. So if I said shape 1 is greater than shape 2, it means the area of shape 1 is larger than the area of shape 2. That seems like a reasonable overload, right? If I wanted to make sure I had a greater than operator. Let's look at linked lists. So we've already looked at linked lists in previous lectures. We're going to keep on sort of plugging away, looking at it from different angles. We had this linked list class. We had a doubly linked list class. If I plus some value on it, I'm not going to use a number. I'm going to use a data type, but it's easier to explain here. If I add data to my linked list, let's say, what I would expect to have is if I call the plus operator, I would expect this data to be added or inserted into the linked list, right? If I said, here's my linked list plus this particular value, I would expect that value to be added to the linked list. At least that's how I'm viewing it. So let's have a look at that code right now. So, nope, wrong one. Here we go. And I think I screwed up and didn't rename this particular project. Hopefully I'm in the right one. I'm hoping I'm in the right one. Otherwise it's going to get real bad. Okay. Let's look at what linked list has. So let's just run linked list and see what happens. Here's our doubly linked list thing. I have a linked list constructor. I call the doubly linked list constructor. We talked about order of operations for our constructors. I'm making all my various nodes for my linked list constructors and doubly linked list constructors. I'm going to print out my linked list. It looks like this. And then I'm going to delete a bunch of these linked list nodes. I have an empty linked list, and then I'm going to delete my linked list. This just happens to be a doubly linked list, but that's fine. In fact, we can actually change that around if I wanted to. Let's go to linked list main and make this a linked list. It's not going to make any difference at all to any of the code. This is what we were looking, or at least hoping for. There you go. I'm making a linked list. I'm calling a bunch of constructors. I still can print off my linked list. I can empty the linked list. I call the destructor. No difference whatsoever. What I didn't tell you is, oh, there we go. Instead of calling inserting at back, I'm just calling the plus operator. Instead of adding it like I did before, inserting at the front or inserting at the back, let's say I add the plus operator. Here's my linked list. I'm adding data 4. Here's my linked list. I'm adding data 5. Data 4 and data 5 are just, some kind of data being stored in my linked list. It could be an integer, it could be a string, it could be anything. And then I'm printing everything out. Nothing has changed to my code. All I've done is call the plus operator instead of insert it back. The reason it doesn't change anything, let's go to linkedlist.h. Here's me defining the new operator. So there's the format. It's not going to return anything. It's when I call plus, the operator plus, then the second parameter, the parameter afterwards, is going to be this, the value to add, and I'm going to do this particular function. This particular function looks like this. Here's the value I'm adding to my linked list. To add is being added to my linked list, and all I'm doing is calling insert at back, and I'm done. But now I have the plus operator ready to go. I've overloaded the plus operator. I'm not doing arithmetic. I'm adding something to a linked list. I'm allowed to do that. This is a form of polymorphism. Let's see if I have another form of polymorphism around here. There are probably lots of different formats that we have. Get start, insert at front, insert at back. I may not have anything polymorphic quite yet. Oh, we could do that. Ooh, I like that. So let's do insert at back. But instead of insert at back, I'm going to do, instead of adding some kind of data, I'm not sure I like that. The insert at back, we could just, instead of inserting something like this, we could call insert at back with just a number. Make my data type on the fly, and then call this particular function. So I'm going to do it, but I don't love the example, but let's try something. Okay. So here's the idea that I'm going to have. Okay, linked list dot insert at back, and I'm going to pass the number 4. That should yell at me, right? I don't have. It's not a data type. It's not this LL data thing. It's not a kind of data. I'm just wanting to insert the number 4. Insert it back in this case would have to make one of these data types. It would have to make an LL data, this thing here. You need to make a type of data, and then it would need to insert that. So with the number 4, it would make an LL data and then insert it at the back. So I'm going to go to my linked list and void insert at back, same name, and then I'm going to have are they unsigned ints? I think they're just ints. Int data val, let's say, and we'll leave it at that. Okay. I'm going to jump over to my linked list. Here's my insert at back. I'm just going to go one line above it. Okay. And what do I want to do here? It's called a LL data to add is equal to, well, I can call it whatever I want. And let's see how that's actually defined, because I always forget these things. And I just LL data to add, and then I'm just going to check change the number. Got it. Where am wrong one. Here we go. To add dot num is equal to data val, and then I'm going to call insert at back to add. That should do it. Let's see what it's yelling at me for. This is an LL data. This is insert it back. Oh, it's a constant. This would be a casting, by the way. It's the fact it's not a constant because I didn't make it constant at the beginning. The constant here means that you're not allowed to modify this variable when I call this function. That's why I have it as a constant here. When I made it initially, I'm not allowed to modify it. I could have done the following. Let's see if I can make this work. To add is equal to data val. Will that actually do it? That should have done it. Oh, it's just assuming I'm adding it. I'm going to do that. Let's put it back in. Fine. I'm honestly stumped at why it's not realizing that I'm trying to do one way or the other. And that should do it. Let's see. That am I getting a inserted? Can I convert from? Okay. I'm just going to make this way. I'm just wondering why it didn't barf on me last time. Actually, let's just bail back a bit and just. I like setting my constants afterwards, so. This isn't a constant, so I can't make that way. Okay, we're still having that problem. Insert it back, insert it back. It's a constant LL data. To add. I should be calling that one. Oh, that's why. I'm surprised it didn't barf on me earlier. Okay. I shouldn't even need that part. I shouldn't need that part. Let's try it now. These are the kinds of things that you can expect. It's not me being absent-minded, although I am. It's these things happen, like you're going to miss a particular thing here. That's fine. It succeeded. Now if I try and insert it at the back, let's have a look. It should change nothing. I've added node 4, which wasn't there before, because now I'm adding a node by just putting in a number. Instead of a data, I can put in a number instead, and it just works. I've overloaded the function. Okay. Let's go back to, so we had operator overloading, we had function overloading. We're going to go back to this and look at some of the benefits at least. So if I know I'm inserting at the back, all my functions about inserting at the back should be called insert at the back, not insert at the back 1, insert at the back 2, insert at the back 3. I just want to have one function name. If it does the same thing in all those circumstances, it should be called the same thing. If all my functions are doing for printing are called print, it's a whole lot easier than print circle, print whatever, print node 1, print node 2. It's convenient. I can have multiple formats. No one needs to know that there are multiple formats. It just works. You didn't know that strings did this. And for operator overloading, I mean, look at the this thing here, the ampersand, whatever the heck that's called, B. There's a proper term for it. Accent circumflex if you want to go with French, but it's not really an accent circumflex. You could, if you're looking at it from a math or logic standpoint, that's A and B. That's the and symbol in math. Or it could be A exponential B if I'm dealing with, or superscript B for text. A exponential B for arithmetic. It's the same symbol in multiple cases. The asterisk is multiple different things. It's multiplies. It's, what else is it actually? The asterisk should be a whole bunch of different things, but I can't think of other things that it's useful for. It's for pointers. I Actually, asterisk is for pointers. It's also for multiplication. Same symbol. If we allow overloading, it allows us to sort of take things from an intuitive standpoint. Adding two strings together should give you the concatenation. We intuitively think of it that way, despite the fact it has nothing to do with arithmetic. Here's coercion. This is casting. This is kind of data polymorphism. So if I have, the implicit format is this, and I think I had somebody in my 1400 class do the implicit version of it a whole bunch of times. They just kept on like adding 2 to it. So if I have a floating point number, f, I can add the number 4 to 2.3, and it will give me a floating point number. Why? Because it doesn't make sense otherwise. So implicitly, I'm going from an integer and a float to a float. Implicitly, the compiler goes, no, you actually want a floating point arithmetic, and it will do it for you. You don't have to manually do it. However, if I have 3 divided by 4, integer divided by an integer, if I don't manually cast something, if I don't explicitly cast something, I get 3 divided by 4 as integer arithmetic, which is equal to, 0, right? I get 3 divided by 4, it's less than 1. I get remainder 3, but it's 0, remainder 3. And the percentage, if I don't do this, the value for percent here is going to be equal to the value 0, because I'm doing integer arithmetic, and then I'm converting it over to a double. So instead I can say, no, I want that 3 to be a double. That's an explicit cast. This is the old school way of doing an explicit cast. This is the way you can do on the exams. I'm not going to pick on new versus old versions of casting. It's really good to learn the new versions of casting, but I'm by no means an expert. They invented it after I was working in industry, so it sort of slips my mind from time to time. The new way of doing it is to say what kind of cast you're doing, like a static cast. This would be a static cast. To what it's going to. So it could be a double, it could be an int, something like that. So this is going to take this number, whatever it is, it's going to statically cast it to be an integer. There are other types of casting as well, but this is a lot more explicit than just saying int. The old school way says int, and you don't know, as it figuring it out how to cast it on the fly. It's a lot more explicit on how you're converting these numbers over with a new version. Casting is really useful. Every time we deal with pointers, we were doing casting. So you can do this new version of casting, or you can do the old version. I would not be offended or upset in the least if you do the new version of casting, if you want to try it out. It involves what kind of casting you're doing and what you're casting it to in the angled parentheses. And casting is just useful because sometimes you need to know, because sometimes our things are equivalent to each other. So the end of a string character, the /0, is the same as 0, which is the same as null, which is the same as false. Or we need to know if it's signed or unsigned, and we have to explicitly cast it. We need this sometimes, and this is another form of polymorphism. Parametric polymorphism is the weird one that we're going to hold off for a little while. It allows you to make an object that takes in a data type t, whatever t is. We will actually do this with our linked list eventually. Right now we have this, LL data type, which is kind of crappy, right? It's only an integer. We want it to be able to take anything. We want, ideally, this linked list to be able to store whatever we want in it. The idea here is a templated data type like class T. What is T? Something or other. It's essentially class, I don't know. That's the kind of data that this takes in. It takes in, I don't know. So if I have max, it takes a function called max. It will return the maximum of A and B and return whichever one's the maximum. Well, what type of class is A? What type of class is B? Well, they're the same type of class. We don't know. We'll have to figure that out later. Compile time polymorphism says, we'll take in any old class you want to give me called A, the same kind of class for B, as long as it supports this greater than operator, we will accept that class. The interesting thing about this is you write it this way. You say, I'm going to have some kind of class T. I'm not going to tell you what kind of class it is. It's a secret. Shh, right? I don't tell you what kind of class it is. But when you call that max function on the fly, when you go to compile it, it says, oh, integers, I know how to deal with that. Or, oh, the rectangles, and you support the greater than operator. I know how to deal with that. As long as you support this operator or whatever function call is being used, it will actually make new code. It doesn't require rewriting the functions. It will actually generate new code, whole other classes of code for you behind the scenes without you knowing. That will, so that it'll make a, if I have a templated linked list class, it will make a linked list class that takes in integers. It might make a linked list class that takes in strings. It might make a linked list class that takes in this or that. It will make a new class for every new distinct type of data being used for this templated class. So when I make a vector that takes in an integer, I will essentially make a brand new vector class that takes in integers. It's weird. We'll have to get into it as another lecture, but it's another form of polymorphism. Parametric polymorphism has a real big benefit in the fact that I have multiple data types. I've defined one function. It can handle multiple data types at once. I don't have to make multiple versions of it. And if I make a new class, it's up to the new that I want to use this thing like a vector. It's up to the new class to accommodate the vector, not the other way around. I don't have to change the vector class. The class that's being used by the vector that I want put in a vector has to change. That's a different way of looking at things, and it's going to be really useful later on. We'll look at this again. So for the meantime, to be continued at a later date, we have compile time or parametric polymorphism. That's another format. So we've looked at these three. The big one is about to come. So I want to pick this up in the next video. Just to take a little break here because I'm going a bit long. I'm long-winded today. We'll look at runtime polymorphism and the weird quirkiness of that. But it's very, very powerful. This is what most people talk about when they talk about polymorphism. So stay tuned because this is what we're looking at. All right. Thanks, everyone.